Okay.
Yes,
So
we see everything.
here we are. I'm going to be talking about the development of quantum error correction, which is really mainly going to be my reminiscences about the early days of quantum error correction. And at the very end, I might say a little bit about the, very, I guess, surprising and interesting new developments, if I have time. So let's see. So the motivation, I guess, is in 1994, I showed that a quantum computer could factor large integers exponentially faster than the best known classical algorithm. And one reaction to the factoring algorithm was, this is never going to work in practice. So why not? Well, Rolf Landauer was a very, eloquent spokesman of this viewpoint, and he said, we have essentially returned to analog computers as foreseen by Asher Perez in remarkably perceptive competence made in 1985. Analog computers can do far more per step than digital computers, but they cannot take very many steps before the accumulated errors have derailed computation. Okay. So the summary of this objection is that quantum computers are essentially analog, and analog computers cannot correct errors. Well, this is certainly true about analog computers not correcting errors, but my rebuttal, which I can only make in retrospect, is that just like quantum objects are both waves and particles, quantum computers are both analog and digital devices. So they can correct errors like digital computers, but they can also do some things like analog computers. So they're very, like the rest of quantum mechanics, they're very non-intuitive. So how bad is the situation? Well, without error correction, to factor cryptographically important numbers, so like the ones that are being used for RSA, you probably have to perform at least 10 to the 9th quantum gates. Now, if you perform 10 to the 9th quantum gates, and you want to have some reasonable chance of your computer giving the right answer, you need to implement each quantum gate with accuracy less than 1 in a billion. And this seems virtually impossible to experimental physicists. And of course, there are lots of computations that would require many more than 10 to the 9th quantum gates. So looked like the situation was hopeless. Well, you can go back and look at what happened with classical computers. In the 1950s, von Neumann showed a very nice paper that you can perform noise-free computations using noisy gates with just a modest amount of extra overhead. Now, von Neumann also went to give a series of talks about this, and in it he mentioned that the brain had to work something like this way because the brain wasn't all that accurate, and it seems to, not break down most of the time. And of course, he got a lot of pushback on this brain thing, but not that much on showing that noisy gates can lead to noise-free computations. So can we make classical fault-tolerant techniques to make quantum computers error-resistant? So at first glance, it appeared the answer was no. So why not? Well, there's a bunch of no-go theorems. There's the Heisenberg uncertainty principle, which says you cannot completely measure an unknown quantum state. There's the no-cloning theorem that says you cannot duplicate an unknown quantum state. And despite these, quantum error corrected codes still exist. So I'm going to try to explain the repetition code, which is the simplest quantum error correcting code, or the simplest quantum error correcting code is the 9-qubit code, but it's the quantum analog of the repetition code. So the repetition code has, in some sense, been known for many centuries. So you just replace each 0 with 0, 0, 0, and replace each one with 111. And if you're fighting an army in, I don't know, Middle Ages, instead of sending one rider with a messenger to your general, you send two riders with a messenger to your general. So if one of them gets intercepted or killed, the other one will get through. So that's just the repetition code. Okay. So what about the quantum version? You can map 0 to the string of qubits and 0, 0, 0. So that's each qubit is in the state 0, and you can map a 1 to the string of qubits 1, 1, 1, where each qubit is in the state 1. So you might object that this is quantum cloning, but it's not, because if you map a superposition of 1 over 2, 0 plus 1, you goes to 0, 0, 0 plus 1, 1, 1. Whereas if you actually had a quantum cloner, it would go from to each state is in the superposition of 0 plus 1. So it's not a quantum cloner, so it's implementable with quantum gates. So this code works against bit flips. So if you have an error which flips one particular bit, it goes, it will take, say, it flips the second bit, it will take 0, 0, 0 to 0, 1, 0, and it will take 1, 1, 1 to 1, 0, 1. So how do you correct it? Well, you correct it more or less the same way you do the classical error correcting code. You perform a measurement which asks which bit is different. And the possible answers are none, bit 1, bit 2, bit 3. And so applying sigma x to the incorrect bit will correct the error. So how do you measure which bit is different? Okay, so I'm not going to give you the quantum circuit that does this, but essentially what you do is you do a projection measurement onto one of the 4 subspaces. So your state will be projected onto one of these 4 different subspaces with probability proportional to the square of the length of the projection. And if it's projected onto the first subspace, then there's no error. If it's projected onto the second subspace, then there's a sigma x error in qubit 1. That's a bit flip error. And the third subspace, that's a bit flip error in bit 2, etc. And now, so you can come up with a simple quantum circuit that performs this measurement. So that's not the hard part. And I want to say that this works for superpositions of encoded zeros and ones, because to make a quantum computer work, you need to fix errors in superpositions of encoded states. So here we have a encoded alpha 0 plus beta 1 qubit. And if there's an error that flips the second bit, it goes to alpha 0, 1, 0 plus beta 1, 0, 1. Now, when this state is measured, the result you get is that bit 2 is flipped. And since the measurement gives the same answer for both elements of the superposition is not destroyed. And that's because you're projecting onto the entire subspace. So if you have a superposition of things in this subspace, then the projection is a superposition of things still in the subspace. So bit 2 can now be corrected by applying sigma x to bit 2. And I want to say that this was realized by Asher Perez in a prescient 1985 paper called Reversible Logic and Quantum Computers, which is actually the same one that Wolf Landauer was referring to in the quote I gave on the second slide. Okay. So to do quantum computing properly, you need to perform more than correct bit errors. You not only have to keep the bits right, you also have to keep the computation coherent. So that means you need to protect against phase errors. So this is a phase error. It's a sigma z, takes a 1 to a -1 and a 0 to a 0. So if you have the superposition alpha 0 plus beta 1, and you got a sigma z error, you would go to alpha 0 minus beta 1, which, although it gives exactly the same states when measured, are the same probabilities of the states when you measure it, it actually would destroy your quantum computation. So Asher-Perez didn't need to worry about this because what he was just doing was trying to implement reversible classical computation on a quantum computer, and you don't need to worry about phase errors when you do this. So now we can ask, what happens with our nice repetition code when you have a phase error? Well, if you have an encoded 0 and you make a phase error on, let's say, the first qubit, the 0, 0, 0 goes to 0, 0, 0 because the 0 gets multiplied by +1 and you get the state E0. And if you if you have a second qubit, the 1, 1, 1, if you have a phase error on any of these qubits, you multiply the state by -1 and it goes to -1, 1, 1, and that's minus E1. So if you make a phase flip error on any of the qubits, you get a phase flip error on the encoded state. And that means if the error rate is low, a phase flip on any qubit gives a phase flip error on the encoded qubit. So phase flips are 3 times as likely. So did this help? Well, not really, because we've squeezed the probability of bit flip errors, but we've amplified the probability of phase flip errors. Okay, so what to do now? I mean, it looks like, well, we need a new idea. So one thing you can realize is that this unitary transformation, which is called the Hadamard transformation, takes bit flips to bit flips and phase flips. I mean, it takes bit flips to phase flips and phase flips to bit flips. And that's just because if you take H, bit flip H, you get a phase flip and vice versa. Okay. So suppose we apply H to the 3 encoding qubits and the encoded qubit. What does this do to our code? Well, we get a new code that takes 0 to the superposition of 0, 0, 0 plus 0, 1, 1 plus 1, 0, 1 plus 1, 1, 0 and 1 to this superposition of, I guess, the complements of these basis states. Okay, so 0 is a superposition of an even number of basis states with an even number of zeros, and 0 is a superposition of the states with an odd number of zeros, and 1 is a superposition of the states with an odd number, with an even number of zeros. Okay. So what happens when we do a bit flip? Well, if we do a bit flip on any qubit, you get a bit flip on the logical qubit, so bit flips are 3 times as likely. But you can correct a phase flip on any qubit. Specifically, if you have a phase flip on bit 3, if you apply it to this guy, you're going to put a minus sign in front of all the basis states which have a 1 in bit 3. And you can note that this is orthogonal to these 2 states. And in fact, it's orthogonal to the bit flip, a phase flip on any one of the 3 qubits on either an encoded 0 or encoded 1. So we can measure which qubit has a phase flip doing exactly the same measurement as we did with which qubit has a bit flip, and then correct this qubit. Or I shouldn't say the exact same measurement, but very similar measurement. So now we have one 3-qubit code which protects against bit errors and one 3-qubit code which protects against phase errors. But the one that protects against bit errors makes phase flip errors more likely, and the one that protects against phase flip errors makes bit flips more likely. And what we really want to do is protect against both phase flip errors and bit flip errors. So what do we do? Well, I mean, there's a technique from classical coding theory, which I guess I learned classical coding theory more or less by osmosis because I was in the math center at Bell Labs, and one kind of research that went on in the math center that quite a few people did was on coding theory. And there's this technique called concatenation in coding theory, and that works here. We can concatenate the codes to get a 9-qubit code. So what is concatenation? Well, first we encode the qubit using one of the 3-qubit codes. Then we encode each of the resulting qubits using the other 3-qubit code. And now the code protects against both phase errors and bit errors. So here, we encode 0 first by the phase flip correcting code, and then each of the 3 qubits we encode by the bit flip correcting code, and that gives the state, 0, 0, 0, 1, 1, 1, 1, 1, 1 here, because the first one takes 0 to, 0, 1, 1 was one of the elements of the superposition that gives you the encoded 0 in the phase flip correcting code, and then when we encode it with the bit flip correcting code, we replace each of the zeros with 3 zeros and each of the ones with 3 ones. So that gives you this code. And this code will correct any phase flip error or any bit flip error in any one of the 9 qubits. And the outer code corrects the phase errors, and the inner one corrects the bit errors. And it's also not hard to say that the code can simultaneously correct one phase error and another bit error. So it actually can correct a sigma y error, which is sigma y is this Pauli matrix, which is I sigma x sigma z. And because it corrects both the sigma x error and the sigma z error, it corrects the sigma y error. Okay, so now we can answer the question, maybe, how did we get around the Heisenberg uncertainty principle? If you measure the error, you disturb the state of the system. Well, we have the state of the computation and the state of the error. And we construct codes where the state of the computation is orthogonal to all the states of likely errors. So that means we can measure any likely error without measuring the encoded quantum state. And then we can just correct the error without disturbing the encoded quantum state. So that's how the 9-qubit code works. And to do this, it requires us to find codes where the likely errors are orthogonal or nearly orthogonal to the encoded states. Well, actually, this isn't the end of the story. I mean, we know how to correct sigma x and sigma z and sigma y errors, but how about arbitrary errors? I mean, there's lots and lots of things you can do with the quantum states. You can do measurements. You can do unitary operations. You can have, you can consider a qubit as an open system and then apply a transformation that, does something even more complicated than these things. And can we does this code correct all of these errors? And there's this theorem. If you can correct an error of any of the following 3 types, sigma x, sigma y, and sigma z, then you can fix any single error that's restricted to 1 qubit. So you can encode your state in 9 qubits. You can do anything you want to 1 single qubit of this 9 qubits, and then you can correct that error. So what's the proof sketch? Well, the proof sketch is an arbitrary 1-qubit error can be written as a 2x2 matrix. And that's more or less true. If you have a Krauss operator on 1 qubit, it's not a mixture of a 2x2 matrices, but it's, it can be decomposed into these separate Krauss operators. And each of these Krauss operators is a 2x2 matrix, and each of these Krauss operators has some chance of happening. So any 2x2 matrix C can be expressed as a combination of the identity, which is no error, and these 3 single qubit errors. And now when we measure the state to identify the error, what we do is collapse the state to one of these 4 possibilities. So either there's no error or one of the Pauli errors. And now that we've measured the state and collapsed it, we know what the error is, we can correct it. So it's this fact that quantum mechanics behaves like either a measurement, which is a discrete or a continuous unitary, is what we're taking advantage of to be able to correct the errors. So it's essentially the same phenomena that means a particle behaves either like a wave or a particle, or maybe I should say a quantum object behaves either like a wave or a particle. Okay, so now we can correct that. Now, suppose we have a better error correcting code that could correct more than one error, because if you look at the history of classical error correcting codes, after the repetition code, Hammond came up with a code that corrected one error, but then lots and lots of people came up with many, many, many different classical codes that can correct many errors. So suppose we have a better error correcting code that can correct more than one error. The theorem, if you can correct any T or fewer errors of the following 3 types, then you can fix any error restricted to T bits. And of course, that's because if you have an error restricted to T qubits, and you do your quantum, and you measure the error using the quantum code, then you collapse the error to a tensor product of T or fewer errors, and then you can correct them. And yeah, so the proof sketch is that you expend the arbitrary 2-qubit errors as a sum of products of T Pauli errors. Well, you can also ask, what about small independent errors on every qubit? Well, you can express the small errors on each qubit as a sum of the identity sigma x, sigma y, sigma z. And if they're small, the component of the identity in there is very large, and the sigma x, sigma y, and sigma z components are very small. And now, when you expand these errors using the distributive property as a sum of k qubit Pauli errors, and the small errors are close enough to the identity, and you have a code that corrects T qubit errors, and most of the mass of the errors, when you expand it in the sum of k Pauli errors, is in errors that have fewer than T qubits, then the error correction process will return a state very close to the original state. Okay, so now I want to go back to, something that I asked when when I first had discovered error correction, and I still find it kind of remarkable. So where is the qubit when it's encoded in the quantum error correcting code? Well, because of the no cloning theorem, there's no redundancy, so there's only one qubit in these 5 qubits that we've encoded it in. And now you know that the qubit is not contained in any of the encoding qubits, because if you completely destroy them, you can still correct the error. So when you encode this qubit in these 5 encoding qubits, well, there's only one copy of it, and it's not contained in any, I mean, no part of it is contained in any single one of the 5 qubits. So, I mean, Landauer had this motto, information is physical, but here the information is, I mean, it's not anywhere specific. It's in the whole of the 5 qubits, but it's not in any one of the 5 qubits. So it's it's mysterious somehow. I mean, with classical codes, you could just say, well, that's because of redundancy that we can destroy a code. But there's no redundancy here because of the no cloning theorem. It's just error is delocalized, or the qubit is delocalized. Okay, so there are better classical codes around. While the repetition code has been known for centuries, better classical codes weren't discovered until 1950. And in 1948, Hamming proved proved that channels have capacities and that you can encode information to send it over channels. But he did, and in fact, he actually showed that good codes exist, but he didn't construct any. He used a randomized argument to show that something was a good code. So I guess after this, Hamming, who was also at Bell Labs, started looking for explicit codes, and in 1950, he published this paper giving the 7-bit Hamming code, as well as a whole bunch of other codes, all of which could correct one error. So this Hamming code, you can map 4 bits, and that's 16 states, that's 2 to the 4th, into these 16 code words. And now, if you have an error, a single error in any of these 7 bits, the code will correct that. Okay. So if a theorem is if a linear classical code has minimum weight D, that's a number of ones in a non-zero code word, or the minimum number of ones in a non-zero code word, and you can correct up to D-1/2 errors. And you can see that this Hamming code has minimum weight 3, and so it can correct 1 error. And the reason it can correct 1 error is that if you have a state with some errors in it, so it's not a code word, it can only be within distance 1 of a code word, because if it was in distance 1 of 2 different code words, then these 2 code words would have distance 2, which isn't possible, because if you subtract these 2 code words, you get another code word, and that has minimum weight 3. So that is why you cannot, you can correct errors in the Hamming code. So what happens if you try to adapt the classical Hamming code to a quantum code? Okay, well, it took me quite a while to figure out how to do this, but here's how you do it. You take 8 of these code words in the Hamming code, and these are actually the code words in what is called, that make the columns of what's called the parity check matrix. And you take the superposition of those, and then you take the other 8 code words, and you take the superposition of those, and the first one, maybe you call it 0, and the second one, maybe you call it an encoded 1. Okay, so this can correct any bit error because, all of these states in the superposition are in the Hamming code, and we can correct a bit error in a classical Hamming code. So what you can do is you can just take this error correction procedure and turn it into a quantum circuit, and now it will correct a single error, a single bit error, single sigma x error in the quantum Hamming code. So how do we show that it corrects phase errors? Well, the remarkable thing is if you apply a Hadamard transform to every qubit of this, you get the same code back. And recall a Hadamard transform turns bit errors into phase errors and phase errors into bit errors. So this code also corrects phase errors. So this quantum Hamming code was discovered independently by Rob Calderbank and me, and also by Andrew Steen. And it's the smallest code in the class of CSS codes. And once you've discovered the Hamming code, it's not so hard to discover the whole class of CSS codes. So I'll tell you a little bit about the CSS code. It's a quantum error correcting code based on two classical error correcting codes, C1 and C2 dual, with C2 contained in C1. So C2 dual here is a set of code words that have dot product 0 mod 2 with all the code words in C2. And the code words correspond to cosets of C2 and C1. And taking the Hadamard transform switches the roles of C1 and C2 perp, and of C2 and C1 perp, which means that if you have a code which corrects T1 errors and a subcode of it, C2, whose dual corrects T2 errors, then the CSS code formed from C1 and C2 will correct T1 bit errors and T2 phase errors. So the nice thing about this is that codes and self-dual codes and weakly self-dual codes and codes which are duals of other codes had been studied extensively by classical coding theorists, and you can now go look at the codes that the classical coding theorists discovered and just grab the ones that give you good CSS codes. So this is how we can get a lot of good CSS codes. And I should say the number of quantum code words is 2 to the dimension of C1 minus dimension of C2. So that's just the number of cosets of C2 and C1, which is the number of code words. Okay. So the next thing of the story was, well, we now have a nice code that corrects 9 qubits and another nice code that corrects 7 qubits. You could ask, are there codes that correct 5 qubits? And 2 groups, one at Los Alamos and one at IBM, decided to look for these codes. And they put the problem on a computer, and they discovered, well, they did not discover a code that looked like this. They discovered 2 codes that were actually equivalent to this by applying Pauli matrices and to the qubits and then permuting the qubits. But the 2 codes they discovered didn't look like each other, and they had nowhere near as much symmetry as this presentation of the code. But the two groups discovered this 5-qubit code. So I was trying to analyze this code. And what I did was I said, maybe I should compute the symmetry group of the code, because that will tell us something about the code. So I asked Neil Sloan how to compute the symmetry group of this code. Well, he said, use the software Magma. And then he gave me a sample Magma code where he had computed the symmetry group of another object that he had been studying. So I wrote the code to compute the symmetry group of this code, and it turned out to be exactly the same size as the one in the sample program Neil Sloan had given me. 5,160,960, which didn't seem like it could be a coincidence. Well, looking more closely, it wasn't just the same size of the group, it was the same group. And looking even more closely, the objects that Niels Sloan was looking at, which were Grassmannian packings, which are packings of, I guess, subspaces or hyperplanes in high dimensional space, were actually very closely related to quantum error correcting codes. So this gave us a clue to find a better description of the code. So what is the better description of the code? Well, the better description of the 5-qubit code is what is, well, it's equivalent to parity check matrices of classical codes, which I haven't told you about, but you have 5 stabilizers here, and you look at each of these rows as sigma x on qubit 1, sigma z on qubit 2, tensor sigma z on qubit 3, tensor sigma x on qubit 4, tensor the identity on sigma 5. And what you want is that all of these row operators given by rows commute. And you can see that because they do in this case, because say in row 1 and row 2, here's sigma z times sigma x. And when you flip the order of these, that gives you a -1. And here's another sigma x times sigma z. And again, when you flip the order of these, you get a -1. So you get 2 -1s. And that means when you flip the order of this row times this row, you get a +1, which means they commute. So this is one of the class of stabilizer codes. And what the code subspace is, the subspace giving the code, is just a subspace that is invariant under all 4 of these transformations. And because you have a 32-dimensional space and 5 operators, each of which has eigenvalue -1 and 1, you end up with a 2-dimensional space, which is your code space. So you can encode a 0 in one of these dimensions and a 1 in the orthogonal dimension in the subspace. So this is a class, one of the class of stabilizer codes. And what are the rules? The rows must form a commutative subgroup of the Pauli group, and the code words are the quantum states that are not changed by the group elements. Okay. Now, you can look at this more closely, and it turns out that the Pauli matrices behave like the non-zero elements of the finite field of 4 elements. And, classical codes are very often constructed over finite fields, and in fact, they're very often constructed over finite fields of powers of 2 because those correspond to bits. So classical codes over GF4 are actually very well studied, and quantum stabilizer codes turn out to be equivalent to weakly self-dual additive codes over GF4, which means you could just go to the literature and look at additive codes over GF4 and find ones that give you good quantum codes. So you can get a lot of good quantum codes by pirating them from classical coding theory. Now, it turned out that you actually need to do a little bit extra in classical coding theory because mostly what people were looking for were linear codes over GF4 rather than additive codes over GF4. But this quantum discovery of the connection of quantum codes to classical codes meant that now classical coding theorists could study additive codes over GF4, and they had a new research area to work in, which was relevant to quantum codes. Okay, so actually quantum error correcting codes are not adequate for doing quantum fault tolerance. You need something more. And what you need is you need to implement gates on encoded qubits without decoding them. So if you implement a gate on an encoded qubit by decoding it, then doing the gate, and then re-encoding it, in the short time that you've decoded it before you re-encode it, you've exposed that qubit or those qubits to error. And that means that, errors will sneak in and these qubits will decay if you're doing a very long computation. So maybe for short computations, you can implement gates by decoding qubits, applying a gate, and then re-encoding them. But for long computations, this is not going to work. So what you need to do is figure out how to implement gates on encoded qubits without decoding them. So what I showed was that you can do n steps of quantum computation if your gates have tolerance 1 minus 1 over log n. And I should say that in classical computation, you can, here's a gate from von Neumann's method of doing using noisy gates to do fault-tolerant quantum computation. If you want to do an AND between two sets of qubits, or two sets of bits, I'm sorry, and this bit, this set of bits is supposed to be all the same, but there might be an error in it, and this set of bits is also supposed to be the same, but again, there might be an error in it. Now you do AND gate bitwise, and you're going to make some new errors in here, but the number of errors in your final state is equal to the number of errors in your original states, plus the number of errors you make when you do this, these ANDs. So if you know how noisy your gates are, you can arrange the number of repetitions so that this is very unlikely to be more than k over 2 errors. And that means that when you clean up these errors, you will always, end up with fewer errors than you started with, or at least if you start with a lot of errors, you will always end up with fewer errors than you start with. And that says that you can do your computation for a very long time because the probability of making an uncorrectable error is very small. Now, for quantum computers, if you have weakly self-dual quantum codes that encode 1 qubit, you can also do this trick of just making the ith qubit of your first code interact only with the ith bit of the second code. And that means that if you have an error in the ith bit of your code words, it's never going to propagate beyond any ith bits. And that means that it will be correctable, because if you have k bits in this one and j bits in this one and make L errors with your quantum error correcting, then at this point you have k plus j plus L errors. And if you've done, you've done your calculations right, that's good enough to correct all. That's good enough that your quantum code will probably correct all of the errors. Now, there is a problem with, so this kind of gate is called a transversal gate. And there's a problem that there's a theorem that you cannot use transversal gates to correct all errors. So, or rather, I'm sorry, the theorem is that you cannot use transversal gates to do a universal set of quantum gates. So you need to do non-transversal quantum gates, and those are where all the complexity comes from. Anyway, I showed that you could do n steps of quantum computation if your gates had tolerance 1 minus 1 over log n. And Aharonov and Benor improved this to tolerance 10 to the minus 6th, which is a threshold theorem, and 10 to the minus 6th is no longer the threshold, it's larger now, but it's also very dependent on your exact model of what your quantum computation, what your gates are, and the architecture of your quantum computer. Okay, And the trick needed for the last step that I hadn't thought of was, again, concatenated codes, which is the trick I used to get from the bit flip code and the phase flip code to the 9-qubit code. Okay. Now, there's a completely different way that people achieve fault tolerance, which is Kitaev, and he uses, well, the easy example to understand is Kitaev's toric code. And what you do is you make a grid with qubits on the edges. I should say that, the toric code is actually one of a large class of surface codes, some of which are, some of which have better properties than Kitaev's toric code. So what you do is you take a torus, so you connect the left side of this grid to the right side, and now you want one code, and then then you want one code that corrects bit errors and a dual code that corrects phase errors. And the bit error code is just the one generated by these crosses XXXX. The phase error correcting code is one course that, actually, I got that backwards. The bit error correcting code is the one that is generated by these ZZZZs. And the minimum distance of this code is the side length of the grid, which is square root of n if you have n bits. And the if you if you put this on a torus, connecting the left to the right, you get a 1 error correcting code. And in fact, you can look at it and figure out that Kitaev's toric code is in fact a CSS code. And now suppose we have a Z error that passes all the parity checks. It must commute with the X parity checks. So what is a Z error? A Z error is a combination of errors on these. The qubits are on the edges, so it's a combination of the qubits of Z, sigma Z's applied to some set of qubits. And if it commutes with all the X parity checks, it must have 2 edges at every, or 4 edges, meaning at every vertex. So that means it's a bunch of loops, or a bunch of paths. So we can ask, well, what Z errors are not correctable? Well, if the path is actually composed of loops, these can be covered by squares. And if you apply a square, a Z to all 4 things of the square, you haven't changed the code state. So that's actually not an error. So the errors are things paths that wrap around the torus. And these paths all have the side length of the torus, which I guess is 4 in this case. And that means if the side length is D, you need D minus 1 over 2 errors to get an uncorrectable error. And in fact, this shows you that there are 2 qubits encoded, one corresponding to paths that loop around the torus vertically, and the other paths that loop horizontally. And by removing some parity checks from the grid, you can add extra qubits to the code at the cost of decreasing the minimum distance. So I'll skip this. I think, what time is it? Oh, I think I have time for this. So, we're now building real quantum computers. And in superconducting quantum computers, you basically put your computer on a silicon chip that has been designed to have superconducting components, qubits on it. And now you can make the 2 qubits that are near each other talk to each other and do a quantum gate. So if you want to class of quantum error correcting codes to put on a superconducting quantum computer, you really want them to be planar codes where the qubits that you have to interact with are close to each other, because that is much easier to do on a superconducting quantum computer. And so these class of quantum error correcting codes that are good for superconducting quantum computers are called surface codes, where the qubits are laid out on some planar, well, I said grid, but some planar graph, and the parity checks are all local. So now I want to do a very quick sketch of some more recent developments in quantum codes. Well, until 2014, all the quantum codes could only correct logarithmically many errors. And then Tillich and Zamor discovered hypergraph product codes, and these are a beautiful construction of codes that correct, well, in their construction, they correct square root of n errors. And yeah, these are the first codes to have larger than O of log n minimum distance. Actually, I guess Gitaev's surface code had over log, had square root of n minimum distance, but only corrected one qubit. And these can correct many qubits with O of root n distance. And like CSS codes, they're constructed by combining two classical codes, but in a completely different way. And what you do is you really take, well, you take the parity check graphs for two codes, and these are the repetition codes. So the parity checks are, you ask, are qubit AI and qubit I plus 1 the same? Qubit I plus 1 and qubit I plus 2 are the same, etc. So these are actually classical codes. And if you combine two repetition codes with a hypergraph product, well, you take the product of this, you get the product of this, that turns out to be a torus, and you get Gitaev's toric code. Now, the interesting thing about this is that the actual parity checks you decide to use make a difference. And using redundant parity checks is different from non-redundant ones. So if you have a repetition code, you don't actually have to check whether the first bit is equal to the last bit, because that's implied if the first is equal to the second equal to the third equal to the fourth, etc. So this is also gives you the repetition code. But now, when you take the product of these with a hypergraph product construction, you get a grid which doesn't wrap around. So it's not a torus, it's a surface. And I didn't tell you this, but you can actually alter the Gitaev surface code so you don't need the wraparound. So you can actually fit it on a quantum computer, and then it encodes one qubit. So depending on exactly how you do the hypergraph product construction with these two codes, you get a surface code, which either encodes one qubit or encodes 0 qubits. So the product of two classical codes with the hypergraph product construction doesn't give you the same thing all the time. And the more recent developments all build off the hypergraph product construction, but whereas the hypergraph product construction is not that difficult to understand, these new discoveries of LDPC codes are really very complicated constructions. So these codes have alpha n minimum distance, where they have n qubits, and they prove the NLTS conjecture of Hawking's, that there are codes which have no low energy trivial states. So if you have codes, then it's going to be correct code is, zero energy. And you can say, well, an error is going to increase your energy. So if you have few errors, then it's going to be a low energy state. But the question is, are there any low energy states that are essentially equivalent to, to the, can be built up very simply from, I guess, the state with all zeros on the code words? And the answer is no. There are codes which have no low energy trivial states. And the reason this is important is if this conjecture were false, then quantum PCPs, which are probabilistically checkable proofs, which are this amazing construction in classical computer science, would be impossible. But the conjecture is true. That means that this argument doesn't show that quantum PCPs are impossible, so they might exist. But it's still unknown whether quantum PCPs exist. And that's where